In this video, I'm going to show you how to find empirical formulas for compounds. Where we left off was finding our percent composition of our different elements within a compound. So we know that if, for example, a certain compound is 75% iron, that 75% by mass of that compound will be iron. So we'll be using our percent compositions today to then determine empirical formulas of a compound. An empirical formula is identified as the lowest ratio you can have between all the elements in a compound. We'll eventually work on what's called the molecular formula, which is like finding the true formula for a substance. These are useful because we can use the percent composition to then determine the empirical molecular formula to ultimately identify materials that are unknown. These are the 4 steps that you work through to determine your empirical formula. So the first step that you're going to do is take your percent and change it to mass. So what we assume in these problems is that your percentage is equal to the number of grams. For example, in this particular problem, we have the percent composition of this diborane. It's 78.1% boron and 21.9% hydrogen. So we can assume that if we have 100 grams of this diborane material, that 78.1% of it is going to be the boron. So again, if you take 78.1% times 100 grams, that's the same thing as saying 78.1 grams. So all I've done here is taken 78.1%, and I can assume that's the same thing as saying 78.1 grams. I'm going to label it with the element that I'm talking about, and in this case it's boron. I can do the same thing now with my hydrogen. So I have 21.9%. I can say that's 21.9 grams of hydrogen. I've completed my first step. The next step is to convert the mass to moles. Again, to do that step, I'm going to set up a conversion factor. I need to line my units up to cancel, and to do that, I need to use my molar mass. So again, you can go to your periodic table to find your individual molar masses of each of these elements. When I use it at my periodic table, I get that boron is 10.81 grams per 1 mole. Hydrogen is 1.00 gram per mole. So your first step is again to cancel these units, so divide grams by grams. So when I do that, I convert them over to moles. This is equivalent to 7.22 moles of boron. This is dividing by 1, still gives me 21.9 moles of hydrogen. That is step 2. Again, the empirical formula is the lowest ratio between the elements in the compound. So you divide by your small. What I mean by divide by small is you're going to divide each of these elements by the lowest amount. Our lowest amount is the boron, so I'm going to divide each of these values by 7.22. Again, what I'm accomplishing here is finding the ratio between these two elements. So 7.22 divided by itself is going to give me 1. 21.79 divided by 7.22, this doesn't give us quite a whole number. So let me show you on my calculator screen what that will look like. So 21.9 divided by 7.22 isn't quite 3. Let me see if I can get this to show up a little bit better. There we go. So by showing that, we get 3.03. And so it's not quite a whole number. Again, what this is doing is we are showing our ratio between the elements that make up the compound. So we can't have 0.03 of a hydrogen atom. We can only have whole amounts of hydrogen. So we're going to round this off to a whole number. And with the rounding rules, this is going to give us 3. So what this tells me is that my ratio between boron and hydrogen is a 1:3 ratio. These numbers become our subscripts. So again, when we did our chemical naming unit and our balancing unit, we never had partials. And so that's why this had to round off. So these are my subscripts. When it comes to writing these in a certain order, I just write them in the order that the problem provides them. So I have boron first. Again, that 1 is implied. We don't write that subscript 1 there. Then I have hydrogen, and that subscript becomes 3. So this is my empirical formula. This is my lowest ratio based on these percent compositions that these two exist at. And so my empirical formula is BH3. The problem is done. The next example is the same premise. The difference between it is we now have 3 elements to work with versus just the 2. So when I started out, I have 32.38% sodium. Again, we assume that if you have 100 grams of this material, 32.38 grams of it will be the sodium. So I'm going to just take 32.38 grams of sodium. I have sulfur. I have 22.65 grams of sulfur. And the remaining percent is oxygen. So I'm going to leave a little bit of space for my conversion. So I'm going to have 44.99 grams of oxygen. The first step to compare them to get our ratio is we have to get them out of mass and compare them to a unit that factors out that they have different molar masses, and that's by converting them to moles. Just like in the previous problem, to make units cancel, I need to divide, so grams need to go in the bottom. Using my periodic table, the molar mass of sodium is 22.99 grams per 1 mole. Sulfur on the periodic table is 32.06 per 1 mole. And oxygen is 16. So I'm still working on step 2 in our steps listed above in the notes. Dividing them out, at this point you still want to keep decimals, so you're going to just round it off to 2 decimals. Sodium comes out to 1.41 moles. Sulfur is 0.71. Oxygen is 2.81. My next step then moves me on to 3, and that's to determine the ratio between the sodium, sulfur, and oxygen. You will always divide by the element that you have the least of, and that would be the sulfur. We only have 0.71 of a mole. So all 3 of these will be divided by 0.71. So the sulfur, we know we're taking itself, divided by itself will be 1. This is where we round things off to whole numbers. So again, just to show you, I'm taking 1.41 divided by 0.71. That gives me 1.985. Again, we can't have 0.98 of a sodium atom. So what I need to do is round it off to a whole number. So that rounds off to 2. When I take oxygen, I take 2.81 divided by 0.71. That gives me an answer of 3.95. That's going to round off to 4. Again, this is my ratio now between my sodium, my sulfur, and my oxygen. Those become my subscripts. This becomes Na2SO4 as my empirical formula. This last problem is very similar in setup, but it's going to have a slightly different result. And we'll see that when we get to our ratio. So it tells us that analysis of a 10.15 gram sample of a compound is known to contain only phosphorus and oxygen. So we're back to looking at just two elements, phosphorus and O. It tells us that the phosphorus content is 4.433 grams, and it wants to know the empirical formula. So again, we're looking for the lowest ratio between these two elements. Well, it tells me directly that the phosphorus content is 4.433 grams of the phosphorus. In the previous problems, it gave you percentages, and we assumed that, again, if you had 100 grams of this material, that 78.1 grams would be the amount of boron. So again, this saves us a step that we don't have to jump from percent to grams. We have all the information we need to work on converting it to moles. However, it mentions nothing about the quantity of oxygen, but we have enough information to determine it. It tells us the sample has a mass of 10.15, and that's for the whole entire compound, the phosphorus and oxygen combined together. This is just my phosphorus, so all I need to do here to figure out my oxygen is take 10.15 grams and subtract the mass of my phosphorus. When I do that, it gives me an answer of 5.717 grams of oxygen. Now I know all my information about each of my elements. Where I go to next is I convert to moles to again work on my ratio. Molar mass is needed. Just like above, oxygen's molar mass is 16 grams per mole. Phosphorus is 30.97. I'm going to divide these out to work on getting my ratio. So my phosphorus is 0.14 moles. My oxygen is 0.36 moles. You divide by your lowest, and so my lowest amount is with my phosphorus. So I divide each of these out by 0.14. So phosphorus is equal to 1. Dividing my 0.36 by 0.14. We're going to see the slight difference here. So again, on my calculator, I'm going to take 0.36 divided by 0.14. So my answer comes out to 2.57. The camera's trying to focus. There we go. So it comes out to 2.57. So unlike the previous problems, it's not very easy to round up nor down. And so we have to keep this half. However, we cannot have a half in our subscript. So what I'm going to do is say that this is equal to 2.5, because again, it can't really round up and it can't really round down. With our ratio, this is same for every 1 phosphorus, there's 2.5 oxygens. So again, I can't have that half oxygen. So our trick of what you need to do in these scenarios to get rid of that half is to double. What you do to one element in the compound, you do to the other. So to get rid of the half, you multiply by 2. And again, because I multiplied my oxygen by 2, I have to do the same to my phosphorus. So this becomes 2 to 5. So that allowed me to get rid of my half and to have my subscripts to whole numbers. I now have all my information to write my empirical formula just like the previous problems. So it becomes P2O5, because again, I couldn't have a partial oxygen in my final formula. And that is how you find your empirical formula.